The Eyes of a Machine: How Convolutional Neural Networks Learn to See. This chapter explores one of the greatest breakthroughs in artificial intelligence, teaching machines to recognize images. The story begins not with computers, but with two neuroscientists, David Hubel and Torsten Wiesel, whose experiments on the visual cortex of cats revealed how the brain processes visual information. Their discoveries later inspired the development of convolutional neural networks, CNNs, the technology behind modern computer vision. Hubel and Wiesel discovered that neurons in the visual cortex respond to specific visual features, such as edges at certain angles. Some neurons detect simple features like vertical or horizontal edges, while others combine these simple features into more complex patterns. This creates a hierarchy of vision, where information flows from detecting basic shapes to recognizing complete objects. They also introduced the concepts of receptive fields, the specific area of the visual field that influences a neuron, and invariance, the brain's ability to recognize the same object regardless of its position or orientation. Inspired by these biological discoveries, Japanese researcher Kunihiko Fukushima developed the cognitron in 1975, one of the first neural networks capable of recognizing patterns. However, it could only recognize patterns in fixed positions. To solve this limitation, he introduced the neocognitron in 1980. This new architecture used simple S cells and complex C cells, modeled after Hubel and Wiesel's findings, allowing the network to recognize patterns even when they shifted position. Although revolutionary, its learning process was complicated and difficult to scale. Around the same time, Yann LeCun became fascinated by the idea that intelligence should emerge through learning rather than being programmed manually. While studying neural networks and machine learning, he realized that the recently rediscovered backpropagation algorithm could train deep neural networks far more effectively than previous methods. Combining Fukushima's architecture with backpropagation, LeCun created the convolutional neural network, CNN, making automatic feature learning practical. The key operation inside a CNN is called convolution. Instead of examining an entire image at once, the network uses a small matrix called a kernel or filter that slides across the image. At each position, the kernel multiplies its values with the corresponding pixels, sums the results, and produces one value in a new feature map. Different kernels learn to detect different features such as horizontal edges, vertical edges, corners, or textures. Unlike traditional computer vision, where engineers manually design these filters, CNNs learn the best filters automatically during training. Each convolution layer contains many filters, allowing the network to detect multiple features simultaneously. Early layers usually learn simple patterns like edges and lines. As the image passes through deeper layers, these features are combined into more complex structures such as curves, shapes, eyes, faces, and eventually complete objects. After convolution comes a process called max pooling. Max pooling reduces the size of the feature maps by selecting only the largest value within a small region. This decreases computation, increases the receptive field of later neurons, and makes the network more robust to small movements of objects in the image. Eventually, the extracted features are flattened into a one-dimensional vector and passed into fully connected layers. These layers act like a traditional neural network, combining all learned features to make the final classification. During training, the network compares its predictions with the correct answers, calculates the error using a loss function, and updates every weight through backpropagation and gradient descent. Over many iterations, the network gradually learns which filters and connections best recognize the images. LeCun demonstrated the power of CNNs by creating LeNet, one of the first successful convolutional neural networks. LeNet recognized handwritten zip codes for the U.S. Postal Service and bank checks, proving that deep learning could outperform traditional image recognition methods. Despite this success, CNNs did not become popular immediately. Computers of the 1990s lacked the computational power to train large neural networks, and software frameworks for deep learning did not yet exist. During this period, support vector machines, SVMs, became the dominant machine learning method because they were easier to use and performed well on small datasets. Everything changed with the arrival of graphics processing units, GPUs. Originally designed for video games, GPUs could perform thousands of mathematical operations simultaneously, making deep neural network training dramatically faster. Researchers such as Jürgen Schmidhuber demonstrated that much deeper neural networks could now be trained effectively. The true breakthrough came in 2012 when Geoffrey Hinton and his students Alex Krzyzewski and Ilya Sutskever developed AlexNet. Using powerful GPUs and millions of labeled images, AlexNet dramatically outperformed every traditional computer vision method in the ImageNet competition. Its success convinced the scientific community that deep learning, and specifically convolutional neural networks, was the future of computer vision. Today, CNNs form the foundation of countless technologies, including facial recognition, self-driving cars, medical image analysis, satellite imaging, industrial inspection, and countless AI applications. Although newer architectures such as vision transformers are becoming increasingly popular, convolutional neural networks remain one of the most influential inventions in the history of artificial intelligence, tracing their origins back to the biological discoveries of Hubel and Wiesel over half a century ago.